Alright, in this video, we're going to solve some questions on source-free RC and RL circuits to look out for things to do, the best practices when solving questions on these topics, so as not to make mistakes and lose out on marks. Alright, so let's get to work. If the switch opens at t equals 0, find v of t for t greater than or equal to 0 and W of C. This W of C is the energy across the capacitor. Across the capacitor, alright? Because you may not always see this, but sometimes questions, after asking you to solve for voltage or solve for currents, they will give an additional parameter to find that you use what you solved for here to get this value. So we have a constant voltage source, 24 volts over here, in series with a 6 ohm resistor. Then after that, a switch. And this switch opens at t equals 0. That's what they're telling us. So the switch opens at t equals 0. That means that for t less than 0, our switch is closed, completing the circuit this way. So everything goes round and comes back. It's simple and it's nice. But for t greater than 0, once t equals 0, the switch opens. And immediately that happens, everything on this side of the circuit gets disconnected. Everything on this side goes, and then you're left with just your capacitor and 2 resistors. So that's what to watch out for. Alright, so it's best practice when you're solving RL and RC circuits, your solution is usually going to be divided into 2 parts. Solving for t less than 0 and solving for when t greater than 0. And each of these have different objectives. When you're solving for t less than 0, you're looking primarily for your initial conditions. So what does that mean? You're looking for V naughts if you're dealing with RC, and you're looking for I naughts if you're dealing with RL circuits. Now, you may not always have to. You won't always need to do this because there are some questions where they will give you assume initial conditions to be, they'll say assume I naughts to be 4 amps or assume V naughts to be 3 volts, something of the sort. So in questions like this, you likely won't see a switch. You won't see a switch. So this switch you see here, like this, that opens at t greater than 0 or closes at t greater than 0. The purpose of this is for when initial conditions are not given. So when initial conditions are not given, you're solving for V naught for RC, you're solving for I naught for RL circuits. So, alright, so then for t greater than 0, you're looking for your effective resistance. R effective, or R Thevenins, it's the same thing. They mean the same thing. Alright, so you're looking for your effective resistance at t greater than 0. And once you get your effective resistance R, remember our formula for a time constant tau is equal to RC for RL circuits, for RC circuits, and is equal to L over R for RL circuits. So this is what we use our effective resistance to find. Once we're done with this, we can plug it into our formula and all will be well. So let's get to solving. So for t greater than 0, for t less than 0, pardon me, our switch is closed. Okay, so we're going to have a circuit that looks like a 6 ohm resistor, capacitor, 12 ohms, this is 4 ohms. Okay, and your 24 volts source at the extreme end. This is 1/6 farads, F ohms, and this is 6 ohms. This is 24 volts. Alright. What is happening? What do we do? What do we do with this information? Remember what we said about capacitors, that our capacitor, when it's connected to a supply voltage, begins to charge up. That means positive charge builds up on one side, negative charge build up. Negative charge is built up on another side. So this means that current can't flow through a charging capacitor. Okay? Meaning your capacitor becomes what you call an open circuit. So what does this mean? It means that you have a point in your circuit where current cannot flow. Let's say for instance, I have a voltage source, then I have a lamp, and then I have like a little switch here. A little switch here. Okay? If this is this way, the way it is, and we trace the current, okay, going this way through the lamp, and it comes to this open junction, the current is not going to be able to flow through this gap, and therefore the lamp will not light up because there's an open circuit over here. But if, for instance, if perhaps we had another lamp in parallel this way, I went this way, this lamp would be able to light up. Okay, this would light up. Once we complete it this way, this will be able to light up. So this will be able to light up, this will be able to light up. As long as the circuit is completed, even though there's an open circuit. What does this mean? When we had just the open circuits, remember this is the only loop in our circuits. It starts from, let's call this 4 volts. So current will start from 4 volts source, meet the lamp, and come here to this open junction and not be able to continue. However, if we give it an alternative path to follow in this lamp and we complete our circuit, then this circuit gets completed and no current flows through the open circuits. However, there's going to be a certain voltage, VOC, the open circuit voltage. So that's what it's called. And this voltage is going to be the same as, let's call this lamp 2, let's call this lamp 1. So this voltage is going to be the same as the voltage across lamp 2 because they're in parallel. They're connected in parallel. So that's how things get done. So to redraw this circuits, we're going to have an open circuit where the capacitor would have been. A 12 ohm resistor will stay the same, and a 4 ohm resistor will stay the same way. Everything else is good, fantastic. Complete the circuits, open circuits, 6 ohms, 24 volts. So what we're looking for now is this voltage. This voltage, V0, that is the open circuit voltage across the capacitor. How do we do that? V0 is in parallel with both the 12 ohm resistor and the 4 ohm resistor. They all share the same node across each other. So they have this in common. They have this in common. So if we find the voltage across the 12 ohms and the voltage across the 4 ohms, they're going to give us the same thing. The best way to do this is to find the equivalent resistance of 12 and 4 so that we end up with one resistor that will be the same as having both of them in the circuits. So once we do that and find the voltage across that new resistor, that's going to be the original voltage, V0, across the capacitor. So the best way to do that, remember we have 12 and 4 ohms. So our equivalent for resistors in parallel is going to be 12 times 4 over 12 plus 4. That's 48 over 16. That's 3 ohms. So the equivalent resistance of the 12 and 4 ohms is 3 ohms. Remember, it looks like we're changing the circuits. It may appear so because we just replaced 12 and 4 ohms with 3 ohms. But what we just did is to find the equivalent so that we can find the original voltage across the capacitor. So redrawing the circuits, we're going to end up with our voltage source, 6 ohms, our open circuits, and now our 3 ohm resistor. Plus and minus V. So now the voltage across the 3 ohms is going to be the same as V0. And we get that with voltage divided times 4. So that's 3 over 3 plus 6 times the voltage we're dividing. So this means we have in series, because ignoring this, you're still going to have a series connection. Okay, let's see if we can even make this clear. To make this a bit more understanding. So we have our 6 ohm resistor and your 3 ohm resistor. So we can get the clear picture. And let's say here, you still have V naught, your voltage across the capacitor. And this is still VC. This is still VC. The voltage across the capacitor. So how we do this is that we multiply this by the original voltage. So that's 3 over 3 plus 6 times V. That's 3 over 9 times 24. 113. I think that's 8. That should be 8. So V naught is 8. 8 volts. Sorry, I had to confirm that. I'm trying not to make mistakes. So V naught is 8 volts. So we know that, alright, the initial voltage across our capacitor went in less than 0 is 8 volts. So this is the same as this is the maximum voltage of our capacitor before the switch gets open. So that's the point. We have the switch closed. We have our switch closed at this point in the circuit. It's closed over here at t less than 0. So our capacitor can charge up to 8 volts. And once it gets open, the capacitor becomes the source in the circuit and starts supplying power to the other components. So this is for t less than 0. Solving for t greater than 0. Now, at this point, our switch is open. Okay, so remember, this is an open circuit. Everything all the way on this left side of the circuit gets disconnected. So we have one over 6 farad capacitor, 12 ohm resistor, and 4 ohm resistor. Remember, we still need to find our time constant T, which is RC, for the source-free RC circuit. And for this, we need the equivalent resistance or the Thevenin resistance. And that's going to be the equivalent of 2 of these. So we can straight up find replace with the equivalence. To solve for that, when we're doing the voltage divider. So that means for t greater than 0,
No, my book does not play himself. I didn't make it dummy.
For t greater than 0, we have 1 over 6 farads and 3 ohms. And what we have to do is very simple substitution. We know that the time constant is RC. That's going to be 3 ohms times 1 over 6 as 1 over 2, or 0.5 seconds. Alright, that's the first part. And that's essentially the greatest hurdle we have to cross when solving for the source-free RC circuits. Now, all we have to do is bring everything together. Remember that we got V naught to be 8 volts. So, substituting, and we remember that V of t is equal to V naught e to the minus t over tau volts. So we can just substitute. That's 8 e to the minus t over 0.5 volts. Since we're dividing by 1 over 2, we can just take that up. So that's 8 e to the minus 2 t volts, which is our formula for the voltage across the capacitor for all time. Remember, they asked us to solve for the initial energy in the capacitor at t equals 0. Okay? And to do that, you know that energy is half CV squared. So since we're solving for at t equals 0, it will be V naught we're going to use. So just substitute half times 1 over 6 times 8 squared. And that's going to give us about 5.3. This isn't quite 5.33 joules. Alright, this is the next question we're going to be solving. Now, as you can see here, okay, in this case, we're dealing with a with an inductor, not a capacitor. That's the first thing we're going to note. Another thing to note is that there's no switch in this circuit. If you look around, you see, oh, we're not given a switch. And why is that justified? Because they gave us the initial condition of the inductor. I naught is 12 amps. So there's no reason to divide to solve for t less than 0 and t greater than 0, since we already have the initial condition of the inductor. All right. Another important thing here is that we're giving the voltage a dependent source, a dependent voltage source, a voltage dependent voltage source. Okay, a dependent source is represented by a rhombus. Okay, you can either have a dependent current source or a dependent voltage source, and they could depend on either current. So if this was 3IA, then this would be a current dependent current source. If this was 7VB, this would be a voltage dependent current source, and the same goes for the current source. So we have a voltage dependent voltage source. So this Vx is the voltage across the 1 ohm resistor. Imagining current flows this way. All right, it's normal to feel kind of wary of questions with dependent sources, but we're going to solve it to demystify dependent sources. So let's get straight to work. The important thing we're going to do now is that since we have a dependent source, I believe the only way we can solve this, or the best way to solve this, is to use our first principles, which means solving as though we're going to derive the expression for this straight from the differential equation. So we're not going to do any fancy substitution. We're going to act like, okay, given this circuit, find the differential equation for this, not substituting from our formula. So I'm going to walk us through how we do that very quickly. So that's plus minus 2Vx, 2 ohms, 6 ohms, 1 ohm, plus or minus Vx, and 2 Henrys. 2 Henrys. All right. Now recall, we're going to use KVL since we're dealing with two loops and want to find the expression for the inductor. So this is going to be I1. This is going to be I2. All right. So let's get to work. For I1, for mesh 1. Okay. 2, the voltage across the inductor. Remember, VL is L di dt. Okay, so the voltage across our inductor is going to be L, that's 2 Henrys, di1 over dt. Okay, plus Vx. Now, let's define Vx now. Vx is 1 times I1. Okay, which is I1. This is going to be important, so we don't make mistakes with our signage when dealing with the second loop. So Vx is I1. Let's keep it as that. Plus Vx, that's plus I1. Plus. So now we have a resistor in between two meshes, a resistor in between 2 loops. How you solve for this is that you add the voltage of the resistor in the loop you're solving for, then subtract from the other loop. So let me explain. That's going to be 2 I1 minus I2. This is because we're solving for mesh 1. We're solving for loop 1. If we're solving for loop 2, it's going to be 2 I2 minus I1. Okay, then plus 2 Vx. Remember, Vx is I1, so that's 2 times I1 equals 0. Okay, let's take this up. Okay, so let's simplify this. 2 di1 dt plus, this is going to be I1 plus 2I1 plus 2I1. That's 5I1 minus 2I2 is going to equal 0. So this is where we stop for the first loop, for the first mesh. Then we solve for the second mesh and make the substitution, and we'll see how nicely that falls in place. So for solving for the second loop, okay, so let me write out for mesh 2. For mesh 2. Okay, oh, excuse my handwriting. Okay, that's a bit better. All right, so let's start with this 6R2, since we're meeting the resistor. 6R2 minus 2Vx. Okay, our current flows this way, and we're going to meet the negative terminal of our dependent source. So minus 2Vx, that's minus 2I2, 2I1. Okay, Vx is equal to I1. Let's try and remember that. Okay, so minus 2I1 plus, remember what we're going to do when we have a resistor in between two loops, plus 2I2 minus I1, since we're solving for mesh 2, now we're going to equal to 0. Let's simplify this. 6I2 minus 2I1 plus 2I2 minus 2I1 equals 0. So that's 8I2 minus 4I1 equals 0. I2 is equal to 1 over 2 I1. All right. We're going to use this too. Just going to throw this into our first equation. Okay, if this is equation 1 and this is equation 2, we're going to throw this in here. Remember, we're solving simultaneous by substitution, so that we can now have a linear differential equation that we can integrate to solve for. A linear differential equation that we can integrate to solve for I0, to find an expression for I1. All right, so let's do that. Substituting that in, di1 dt plus 5I1 minus 2, 1 over 2 I1 is equal to 0. So this 2 cancels out, so I'm going to end up with 2 di1 dt plus 5I1 minus I1 equals 0. Okay. To the I1 dt plus 4I1 equals 0. Let's simplify this, dividing both sides by 2. di1 dt plus 2I1 equals 0. Okay? So now we have something that looks familiar with how we derive the expression for the source-free RL circuits. We can do that now. So let's isolate them. We'll take this to the other side. So the I1 dt is equal to minus 2I1. Okay, divide both sides by I1. So that's 1 over I1. The I1 is equal to minus 2 dt. Okay, so that's legible. Go to minus 2 dt. Alright, so integrate both sides at t equals 0 and at time. Okay, same here, 0 and time. So that's going to give us ln I of t minus ln I0 is going to be equal to minus 2t. Then we can do this for t and 0. How this works is that we're integrating with definite limits. All right. So when the time is 0, this tends to 0. So if we were going to simplify this, we do minus 2, 0, minus t. Am I doing this right? Okay. And minus t. Ooh. No. To simplify the definite integral, we're just going to, this is the final term, this is the initial term. Okay, so this looks like a plus. This is t for time. Alright, so simplifying this first as minus 2t. Okay, and subtracting minus 2, then letting t equal 0 times 0. So this goes away, I end up with minus 2t. Okay, so this all simplifies to minus 2t at the end of the day with the definite integral. So the trick from logarithms that this becomes, you can make this a fraction. So then I of t over I naught is going to be equal minus 2t. All right, remember how we simplify this? Make both sides exponents of e. So that's going to cancel the limit. So you have I of t over I naught is going to equal e to the minus 2t. Okay, where do we stop? I of t all over I naught is going to be equal e to the minus 2t. Okay, we can simply take this to the other side. I of t is I naught e to the minus 2t. Remember they gave us I naught as 12 amps. Now we have our expression for the current through the inductor. So 12 e to the minus 2t. As simple as that's amps. An important thing to note, if you ask for the time constant, it may be easy to call this the time constant. But remember that the formula, the exponent is minus t over tau. The time constant is going to be 1 over 2. Okay, just keep that in mind to avoid mistakes. The third problem we're going to be solving is, again, with an inductor. All right, now we have a switchback. We're not given initial condition. So what do you see here? We have a 24 ohms resistor, a 15 amp constant current source. All right, now we have a resistor configuration here. 12 ohms, 8 ohms, and then 5 ohms across both of them. And then we have our inductor nicely tucked here away in the corner. And we have to find I of t. Take note of the current direction. I of t for t greater than 0. All right, this may look complex. It does look a bit tricky, but let's solve for this and show why it's solvable. Remember, now that we're not given an initial condition, we're going to divide our solution for t less than 0 and for t greater than 0. Okay, so for t less than 0, remember what we're looking for is our initial condition I naught. Okay, so that's the current to your inductor at the beginning. So when you're finding the initial condition, capacitors become open circuits. Okay, and your inductors become short circuits. So these are both electrical faults in a sense. You denote open circuits, something like this, okay? No currents can flow through an open circuit, but you will have an open circuit voltage, VOC. These are open circuits. But for short circuits, okay, you can denote them sort of like this. This is when you have a very low resistance element. So low you can practically call it an element of zero resistance, shunting in parallel with other components. So when current meets a branch, so we have current flowing in this direction, and it meets a branch that has a straight wire and a resistor. What's going to happen is that your current is going to ignore this resistor entirely and flow through the short circuit and continue on its journey. So this becomes a short circuit fault. So that's what inductors become. So usually when you're solving for t less than 0, your capacitors become open, your inductors become short. So let's see how that affects the circuits. Okay, so for t less than 0, we're going to have to redraw 24. We can do it with our switch since we know it's going to be closed. We've seen amps. 12 ohms, 8 ohms, 5 ohms, and we have our short circuit here. Okay, you don't have to draw these circles, just to remind us that, okay, this is a fault. 24 ohms, 15, 12, 8, 5, and this is I naught. So what's happening here? Current leaves our 15 amp source, okay, and gets to this junction. It's to divide to 24, divide to the right hand side accordingly, okay? Let's go this way, all right? It gets to this junction, this node. Let's remember, we met this node, divided, met this node, it will divide again accordingly. All right, and once it gets to this node, remember what we said about the short circuit fault. This is a line, a straight wire with no resistance, and this is a load. So the entirety of the current that enters through the 12 ohms is also going to ignore this 5 ohm resistor and continue along this path. So this becomes shorted out. The term for this is shorted out. It's kind of a way to inspect complex, dangerous elements in a circuit you don't want to turn off. So let's say we have an element here that we want to do maintenance on or want to inspect, but we don't want to turn off the entire circuit. We can just connect a shunt. We can just short it. We can just short circuit it. All right, so that means this becomes dead entirely because any current that comes here ignores it at this node and goes straight through here. So that means our 5 ohm resistor becomes entirely futile. Performs no function. Okay. So that means we can also redraw this again to end up with a very nice looking setup. This is our 24 ohms. Let's give it a straight line. Our source, our 12 ohms, and our 8 ohms. So this is 12, 8, pardon me, that's 8. This is 12, this is 15, and this is 24. Okay? And remember, recall, I naught flows to the 12 ohms branch, because remember, it meets here, all the current that enters here still continues along this line. So I naught is still the current that flows to the 12 ohms, as long as t is less than 0, because only then is it a short. So what we're going to do here is the current dividing principle. Remember for the first question, we had to divide the voltage. Now what we're going to do is called the current dividing principle. And usually, let's say we have resistors A and B, and we have a current, big I, coming in, and we want to find the current through A. Alright, so I of I through A is going to be the value of B times big I. That's the dividing. Alright. Now when you have three elements, it's going to be it's the same concept. We're going to be a little trickier. Let me help us with this. But it's easier because we don't have to resolve and then expand again. So how this is going to be, let's say now we're dealing with 24 ohms, 12 ohms, and 8 ohms. The I naught, let's say the I through 12. I naught is, let me erase this. I through 12. I through 12 is going to be 24 times 8. So we're going to multiply the other two resistors, their values. So 24 times 8. Okay. Then our denominator is going to be the product of each of the resistors, but that appears only once. So we're trying not to duplicate elements. So that's 24 times 12 plus 24 times 8 plus 12 times 8. So this is a very simple and straightforward way to get the current through the 12 ohms resistance very, very simply and straightforwardly in a straightforward manner. So let's resolve this. 24 times 8. I'm going to give us 192 all over. Oh, I have to do this at once. 24 times 12 plus 24 times 8 plus 12 times 8. Alright, so that's going to give us 192 over 576. And that's conveniently is 1 over 3. Alright. Now, remember that this is just the coefficient. We're going to now multiply this by the total current that enters, so times 15. Okay, so 1 over 3 times 15. We now know that the current to the 12 ohm resistor is 5 amps. And this is our initial current through the inductor. Okay, hope you understand what we did. We ended up with, we realized that the inductor short circuits out the 5 ohm resistors. So we end up with a parallel connection of 3 resistors, 24, 12, and 8. We then use current divider to find the currents, do the 12 ohms, and analysis shows us that that is the same as I naught. Alright, so we've done the mammoth parts of the work. Now we're going to have to solve for t greater than 0. Okay, remember what we're looking for now is our effective resistance that will help us get our time constant, tau. So remember, this entire left side of the circuit gets disconnected. We're going to end up with only this configuration. We'll separate our work. So that's going to be 12. It's important to note that now that we're solving for t greater than 0, your inductor is back in action. Your capacitor becomes back in action. Alright, since you're solving for t greater than 0, that means your source has been disconnected. Okay, so that means this 5 ohm resistor is not shorted out. So it's just 2 henries. It's just an important point to note. So we will see that 5 ohms, this 5 ohms resistor is in parallel with both 12 and 8 together. So finding the equivalent of 12 and 8 in series, that's going to be 20 ohms in parallel with 5 ohms. And then let's leave it this way. Or we can just bring it down. Since this is going to be along the same loop, we can take this here. It's still the same circuits. At 2 henries inductor. This is 20. This is 5. Okay, we can now find the equivalent of 20 and 5. It's going to be 20 times 5. Right. 20 plus 5. Okay, that's going to give us 4 ohms. So now we're going to end up with a very simple and delicious looking setup. A 2 henry inductor connected with a 4 ohm resistor. That's 4 ohms. This is 2 henries. And we can do this very simply for here. Our time constant, tau, is going to be L over R. That's 2 over 4. That's 0.5. Okay? And remember that. Then I'm not do that. Remember that our initial current I naught is 5 amps. So we can put that into our general expression. I of t for all time is I naught e to the minus t over tau. Okay? So that's going to give us 5 e to the minus t divided by 0.5. We're dividing by half, so we can take 12. So that's going to be I of t is 5 e to the minus 2t amps. Very simple.